Hello, my name is Ivan Morrow. I am presenting on my final project for ECE 528. Um, my project is titled Optimizing Attention-Based Image Classification for Edge TPU, um, and with a focus on performance analysis from the training side all the way to deployment and inference. Introduction, the goals of my project were to develop a training pipeline that was optimized for TPU utilization with a focus on parallel processing. Uh, I also wanted to fine-tune an image classification model targeting deployment on an edge TPU device, which I have right here, um, and to implement an attention mechanism in the fine-tuned model and deploy that attention mechanism in the model to the device and perform inference on it. So the base model for my project is the MobileNet V2 model created by Google. Um, this model is designed for image classification in constrained environments like smartphones and the Edge TPU device. Here, this is just a picture of the base model architecture. The data set I'm using is the TF Flowers dataset from TensorFlow. So with this dataset, what I'll be doing is building an image classification model that can identify or classify five different classes of flowers from this dataset. It's got about 3,670 images in total, and the five different classes of flowers in the dataset are daisies, dandelions, roses, sunflowers, and tulips. So, data pipeline and training optimizations. The data pipeline was created with TPU optimization and hardware efficiency in mind. I trained the model in Google Colab environment with TPU runtime. Some key features of the pipeline are utilizing the TF record data format, which is a data format offered by TensorFlow. Under the hood, it uses protobufs, which is a way of serializing data into binary format, which makes uh, it a lot easier to do batch loading and batch processing. It also cuts down on the size of data, so that's very helpful when you're working with large data sets and large data types like images. Parallel processing. Wanted to really utilize all the cores available to me in the Colab environment, and TPUs were designed for this specific use case in mind, so I wanted to put them to the test. Um, TPU and TensorFlow configuration via the TPU cluster resolver TensorFlow API. Um, just selecting the TensorFlow or TPU runtime does not automatically execute your operations on the TPUs as efficiently as possible. So I really wanted to make use of the API to do that. And then dynamically scaling the batch sizes with the number of TPU cores. This is a very interesting part of the pipeline. Basically, in the training portion, we pass in batch size and we essentially multiply the batch size by the number of TPU cores available to make sure all of the TPU cores have data to operate on all the time. So some more optimization. The model architecture was designed with power of two dimensions because TPUs are designed to work well with those. Um, so yeah, the resource utilization is maximized through dropping drop remainder batching for a consistent TPU execution, parallel data preprocessing across multiple cores, and memory aligned computations with optimal TPU performance. So these optimizations resulted in a significantly more performant training pipeline than a traditional pipeline, not utilizing parallelism in TPUs. I ran performance benchmarks against the TPU optimized pipeline and the traditional pipeline. The TPU pipeline finished training in half the time, and the TPU pipeline throughput is where it really shined. It was capable of processing 11,355 images per second, and the non-optimized pipeline could only process 142 images per second. So the model architecture, I included an attention layer in the model, um, and so the attention layer focuses on learning which features are most important, specifically for the flowers. It could be the petals, could be the stem, the color. Basically, it builds this attention weighted feature matrix and then passes that on to our classification layer. So I really wanted to show that we could incorporate an attention mechanism on an edge device like the TPU. So the benefits for an attention layer and flower classification are that it can learn what features are relevant versus what is not. Some flowers have very distinct features. The attention layer will learn how to emphasize those different features, and then it also learns to ignore features that are less important. Um, so after compiling the model and converting it to a TF Lite model, we actually also have to do some post-training quantization. This is to make it compatible with the TPU, the Edge TPU device. It has very strict requirements. It only supports 8-bit integer operations, and it can't run normal TF Lite models. So here, this is just the code for quantizing the model. So the Edge TPU requirements are that they have the parameters have to be 8-bit quantized. Tensor sizes must be constant at compile time. The model params are constant at compile time. Only one, two, or three-dimensional tensors, and the model should only use operations supported by the Edge TPU, which has just a small list of operations that it supports. Um, After you have quantized the model, you've converted it to a TF-Lite file and then quantized it. Then you also have to pass it through the Edge TPU compiler, which is a CLI tool created by Google to compile files to make them compatible with the Edge TPU. You can install the compiler locally or run it via public notebook, which is what I did. Um, the compiler basically just verifies that the given model meets the requirements we just discussed in the prior slide. And if it doesn't meet the requirements, it can still compile, but then only a portion of the model will be run on the TPU. The rest will be siphoned off to the CPU, and you'll see massive performance degradations from that. So the Edge compiler, it optimizes the model for efficient inference on the Edge TPU. It converts the model to the Edge TPU's custom instruction set and applies graph level optimizations like operator fusion, um, etc. So this is what the workflow looks like for an Edge TPU model. You can see there's the original model, 32-bit float numbers. You can do quantization aware training, which is actually the recommended way to deploy a model to the TPU, the Edge TPU device. I did not do this because it makes training a little more complicated. But you can see the post-training quantization is also applicable, converted to 8-bit quantized, and then you compile it to an Edge TPU model and then deploy it. So after compiling, we ended up with a model size that was 4.49 megabytes. Um, all the model params fit within the on-chip TPU memory, which here you can see the output from when I compiled it. Um, so this means all on-chip memory used for caching model parameters. This means this is the amount of space we took up from the parameters on the TPU, and the off-chip memory used for streaming uncached model params is 0. That means all the model params fit on the TPU, which is really, really good. Number of TPU subgraphs is 1. That means there's really a subgraph is the flow of execution um, of the model on the TPU. Since this is 1, we know that the entire uh, model fit on the TPU, which is really, really good. Because if it didn't, we would see multiple subgraphs, and then that's when you end up with some operations executed on the CPU versus the TPU, and you don't really fully utilize the TPU hardware. So here we can see just some accuracy comparisons of the model running in the cloud TPUs versus the edge TPU. On the cloud in the Google Cloud Notebook, the test accuracy of the model was about 90%, but that was without quantization. After quantizing and compiling and deploying on the edge TPU, We got about 89% on the accuracy on the test data, so only about 1.4% less than in the cloud, which is really good. And then here's some stats on the inference on the device. Only average inference of about 3.6 milliseconds and a throughput of about 271 frames per second. We also utilize warming up on the Edge TPU because the model's first inference can take a lot longer from a cold start if it isn't already, performing some operations. So we can warm up the model by feeding dummy data into the model. But just before we feed in some real data we want to inference on and perform optimally. So this is the difference between the first different inference on cold start was about 18 milliseconds versus 3.44 milliseconds when warming up versus not. So conclusions, we can deploy attention-based mechanism models on edge devices. This is a very, very small example. I wouldn't expect this to scale up to certainly not like the LLM-based attention or transformers. Um, but it's kind of cool that something that's very popular, like the idea of attention, can be deployed on an edge device. TPU optimization can go a very, very long way, especially with parallel processing and data pipeline. And I'm sure this applies to other hardware accelerators as well. It's just TPUs are most accessible. So it's very cool to get to utilize that and see all the support that TensorFlow has for this parallel processing and TPU specifically. So I learned a lot about TensorFlow that I didn't know before. The Edge TPU is a powerful AI accelerator in very, very small form. Um, and there's very minimal accuracy loss in the quantized model deployed on the Edge TPU. So that was very exciting to see. Some potential improvements would be to use the TPU optimized data pipeline for a much larger data set. The throughput was really, really impressive. Just the data set I was training on was not that big. And I don't think we really solved all the benefits we would have if we had a very, very large data set. So I'd like to see what that pipeline can do with a much larger data set in a uh, yeah, much larger data set and just doing even more parallel processing. Um, I'd also really like to deploy a larger and more complex model to the TPU. Um, the image classification is relatively a relatively simple uh, model, and so there wasn't extremely difficult to get it running on this device. So doing something a little more interesting like object detection would be a lot of fun. I'd really like to utilize the full benefits of the TF record format in the training pipeline. We don't actually utilize the streaming data directly from TF records in the pipeline. Just didn't have time to implement that, but that's really where that data format shines. So it'd be cool to try that out. Really like to utilize TensorFlow graphs more on the inference side. We utilize it a lot in the pipeline, but don't really utilize it in the inference. And I really love to go through some of the tutorials on the Coral website for deploying C++ models to the device. So yeah, that is my presentation. Thank you.